Welcome to Lab 5 of our Signal Integrity Basics series. For this lab, we will delve into the world of differential pairs, a basis for high-speed digital design. These carefully matched signal paths are crucial for maintaining signal integrity in noisy environments and for transmitting high-speed data reliably. The objectives for this lab are to understand how to create and configure different pairs within a schematic, to explore the concept of odd and even modes of propagation, and to utilize the Stackup Editor for effective impedance planning of differential pairs. A differential pair consists of two traces, ideally carrying signals that are equal but opposite. Because the current flow is in opposite directions, their electromagnetic fields couple, which help contain the signal energy between the two traces and reduces how much noise they radiate into the surrounding circuitry. This inherent coupling provides noise immunity. Any external noise that couples into the differential pair tends to couple equally into both traces. Since the receiver measures the difference between these two signals, any common mode noise is effectively canceled out. To function optimally, these traces are routed with controlled spacing and precisely length matched, ensuring that the pair behaves as a single, robust transmission line. We will start by invoking Siemens HyperLynx SI. Navigate to your SI Basics lab directory via Windows File Explorer. Double-click the Launch HyperLynx SI icon and confirm the licensing dialog. Next, we will open the schematic file pertinent to this exercise. Select Browse, Line Sim Projects, Open Schematic, and locate the directory from the HyperLynx Workshops folder. Then we'll open up the file diffpair.ffs. From the diffpair's 100 ohm set of transmission lines on the schematic, we will now examine their electrical properties. Double-click on TL1 to invoke the Edit Transmission Line window. Select the Transmission Line Type tab. Here, observe that the coupled type is set to Stackup. A stackup refers to the precise arrangement of copper layers and dielectric materials that constitute a PCB. It defines the thickness, spacing, and material properties between layers, which in turn directly determine critical electrical properties like impedance and capacitance. A stackup transmission line means our signal trace is modeled precisely within this defined PCB layer structure. On the right side of this window, you'll see various transmission line properties displayed, such as the characteristic impedance, resistance, and delay. These properties are dynamic and will automatically update as you make changes to the physical parameters. The Hints section also provides valuable insight into choosing the appropriate transmission line. Now, navigate to the Create, Edit Coupling regions. Here, you can see and modify the physical attributes of this coupled line, like its length, the individual trace widths, and the specific PCB layer that it routes on. These are all editable values that directly influence the pair's electrical behavior. The Impedance window dynamically displays the impedance of each individual transmission line, along with the differential impedance of the pair. This differential impedance is a key parameter for differential signals. Let's try to match the target differential impedance of 100 ohms. With TL1 selected in the coupling regions, change its length to 1 inch. Notice that the differential impedance in the impedance window does not change. This is an important concept as the impedance of transmission lines is determined by their cross-sectional structure and the electromagnetic properties of the surrounding materials, not by their length. Now, change the trace width to 6 mils. Observe that the differential impedance is now 100.2 ohms, very close to our 100 ohm impedance goal. Impedance matching is vital in differential pair design. It means carefully designing the traces so that their differential impedance precisely matches the impedance expected by the driver and receiver. Any mismatch will cause reflections, leading to signal distortion and a reduction in the eye opening of an eye diagram, which directly impacts signal quality and timing. Now, let's delve into the odd and even modes of propagation, which are a fundamental part to understanding differential pair behavior. Go to the Field Solver tab to review the EMI fields in odd mode. Ensure the propagation mode is set to differential, plus and minus. This configuration represents the odd mode. Click Start to enable the EMI simulation. Observe the red lines, representing magnetic field lines, and the blue lines, representing electric field. In odd mode, you'll see the fields are largely concentrated between the two traces, with minimal external radiation. This is the desired behavior for a differential pair, as it signifies good coupling and containment of the signal energy. Next, let's simulate the EMI fields in common mode. Change the propagation mode to common, plus plus. This represents the even mode. Press Start, and notice the dramatic change in both the electrical and magnetic fields. In common mode, the fields extend much further out from the traces, indicating significant external radiation. This illustrates that when elements in the differential channel become imbalanced, perhaps due to mismatched lengths or different loadings or asymmetries in the return path, some of the differential signal energy can convert into common mode signal. This is known as mode conversion. When differential energy converts into common mode, the pair loses its symmetry. Both traces effectively carry the same voltage or current instead of the desired equal and opposite signal. This makes the pair far more vulnerable to external noise, increased EMI radiation, and can cause increased reflections and jitter. Odd mode is the desired behavior, while even mode is an undesired byproduct created when a differential pair loses its symmetry. The impedance for each mode is calculated differently. Differential impedance is approximately twice the odd mode impedance, while common mode impedance is approximately half the even mode. These theoretical relationships can be verified directly from the numerical results provided by HyperLynx. To confirm these impedance relationships, select View in the Numerical Results section. This will invoke the HyperLynx file editor. Locate the differential Z, odd mode Z, and common mode Z, and even mode Z values. Compare these values with the equations we just discussed. You should find that they align perfectly. Once you review these values, close the HyperLynx file editor and the Edit Transmission Lines windows. Now, let's explore how to plan differential impedance using the Stackup Editor, a powerful tool for designing your PCB layers. Select Design Setup, Stackup, Edit Stackup. In the Stackup Editor window, click on the Z0 Planning tab. Here, we can define our impedance goals. Select Plan for differential pair and set the strategy to solve for both. This tells the tool to calculate optimal trace width and separation for a given impedance target. In the table, ensure that the differential Z0 for layer top, which is in row 2, is set to 100 ohms. This is our target differential impedance for traces on that top layer. Click View on that row for the Z0 curve column and the top layer. This action will open up the width versus separation plot, specifically for this trace. This plot is a graphical representation of all the combinations of trace width and separation that will yield this target impedance. As we hover our mouse over the plot to review different values for the width and separation, you'll notice that for this specific layer, a separation of 10 mils and a trace width of 6 mils will achieve a differential impedance very close to 100 ohms. This is a microstrip configuration, meaning that the traces are on the outer layer with a reference plane below. Let's close out of this window and compare this to an inner layer. Click View on row 6 in the Z0 curve column for inner layer 1. This will open up a new width versus separation plot, again for 100 ohms for a different layer. Hovering over this new plot, we'll notice that this is different from the top layer plot, even though the impedance goal was the same. The difference is crucial and highlights the impact of the PCB stackup. The local electromagnetic environment around these traces is not the same as it was at the very top. This environment depends on several factors: dielectric constants of the surrounding materials, trace thickness, and the distance to reference planes. Traces routed on the top layer are typically considered microstrips. Part of their electric fields travel in the PCB dielectric and part in the air above the board. These multiple environments means that the signal experiences multiple effective dielectric constants. In contrast, traces routed on inner layers of the PCB are called strip lines and experience a single, consistent dielectric constant as they are fully contained within the PCB dielectric. Let's see how changing the layer thickness impacts this plot. Close out of the width versus separation plot, and in Stackup Editor, change the thickness for line 6 from 1 to 0.5 mils to match the layer thickness of the top layer. Now click View on row 6. Notice how the plot is different from before, but still not exactly the same as top layer's plot. This confirms that there are other factors, such as the surrounding dielectrics and the distance to the reference planes, that are impacting the traces on this inner layer. From this plot, we can determine that at a separation of 10 mils, the trace width should be around 4 mils to achieve a differential impedance of 100 ohms on this specific inner layer. This information is incredibly valuable for routing your actual PCB. Close the Stackup Editor. And finally, let's apply this knowledge to editing a differential pair on an inner layer. Double-click on TL3 on the schematic to invoke the edit transmission line for this trace. Ensure that this differential pair is indeed on layer 3. Based on our differential impedance planning, set the trace width to 4 mils and the trace-to-trace separation to 10 mils. Observe the differential impedance in the impedance window. It should now be around 101 ohms, very close to our 100 ohm target. This demonstrates how effectively the Z0 planning tool helps you achieve precise impedance control based on your stackup and design goals. To conclude this exercise, we have gained an understanding of differential pairs. We've seen how their unique construction provides inherent noise immunity and reduces EMI through cancellation of electromagnetic fields in odd mode. We've also explored the detrimental effects of mode conversion to common mode when symmetry is lost. Crucially, we've learned how to leverage the Stackup Editor's Z0 planning capabilities. This helps us accurately determine the physical dimensions, trace, and separation required to achieve differential impedance on different PCB layers. This knowledge is fundamental for designing reliable, high-speed interfaces. By carefully controlling impedance, understanding propagation modes, and utilizing tools like HyperLynx, we can ensure that differential signals maintain their integrity and perform as intended.